Hello to everyone. My name is Sajjan Pokhrel. I am a student at the University of British Columbia in Vancouver, Canada. The topic of my today's presentation is a sustainable heating solution for multifamily residential buildings in cold climates. It is a case study of a Canadian building for which we propose a green heating solution. Now, without further ado, I would like to take you to the proposed construction site. Okay, this is the satellite image of the location, and the total area of the building is 73,500 square meters, of which 35,000 is available for solar system. There will be two buildings, building A and building B, and totaling of 826 apartment units. There is a municipal sewage line system that runs 40 meters beneath the site. So the idea is to utilize the low-grade heat from this sewage line to meet the thermal demand of the building with the aid of heat pumps, right? But as we all know that heat pumps can be effectively used to improve the quality of heat from sewage line, but at the same time the compressor of the heat pump requires electricity to function. So a solar PV system with lithium-ion battery storage is proposed to supply the electricity to the heat pumps to make the building 100% green. Okay, in this slide I discuss about the techniques that we used to model the system. There are basically four components. The first one is the estimation of the building thermal demand. Building thermal load accounts for the energy needed to heat the fresh air and heat losses from the building from walls, windows, doors, roofs, ceilings and floors, and accordingly it also accounts for the hot water consumption in the building. The second one is the design of the sewage heat recovery system, which basically consists of designing the heat pumps and designing the water pumps. The heat pumps COP, or the coefficient of performance, is calculated based on the evaporator temperature and condenser temperature, while the pumping power is designed or calculated based on the desired sewage flow rate to run the system. The third component is the solar PV and the battery system. It is designed based on the availability of irradiation at that location and keeping in mind the worst case scenario, which is the month of December, because December has the lowest irradiation availability and the maximum power is needed to lift the water to the surface in the month of December as well. And finally, economic evaluations are performed, which is basically calculating the capital cost, cost of energy, energy savings per year, and the payback period. Now I would like to take you to the results section. The first result is the thermal demand of the building. The picture represents the building monthly heat demand. The annual heat demand is 20 terajoule, and the highest heat demand is for the fresh air heating, which is followed by the envelope heat loss and followed by the hot water demand of the building. The month of January has the highest heat demand, while the month of July has the lowest. And these are the results for sewage system design. This diagram depicts the total number of heat pumps required and their corresponding COPs for different months. And the heat pump that is used in this analysis has the rated power of 95 kilowatts, and the COP of the heat pump varies between 3.6 and 6.4 depending on the temperature of the sewage line. Similarly, the total number of heat pumps in use ranges between 1 to 5, again depending on the month of the year. And the figure on the right represents the amount of electricity that is required to run the system. The compressor consumes the majority of the electricity, while the water pump also consumes some power. Similarly, this slide presents the results of solar power generation and the economic findings. The figure to the right side of the screen depicts the energy generated from the system for each of the months, because the solar system was designed for the worst case scenario, which is the month of December. Extra energy is generated in all months other than December. and this extra power and energy will be used to power other electrical appliances throughout the building. And also the main economic findings include the proposed system cost estimation, energy savings, payback period, and according to the table, the system's total capex is 22 million, while the annual savings is 0.8 million. As a result, the system's payback period is 26 years. So going to the conclusion, this study proposes a renewable heating solution for a residential building with 826 apartments. The sewage heat recovery system and solar PV system are primary energy sources. The total number of heat pumps required is 5 with COPs ranging in between 3.6 to 6.4. The total area of PV modules will be 26,000 square meter and the system payback period will be 26.6 years. Thank you so much.